Hello everyone, welcome back to the channel. So today we are going to start covering the neural networks. First we're gonna start with the recurrent neural network or the RNN. So first of all, what is RNN? Unlike a feed-forward network which treat every input as independent, an RNN maintain a hidden state HT that gets updated at every time. This lets the information from the previous input influence on how the current input is being processed. Here's the core insight about it. The network reuses the exact same weight at each single time step. The hidden state act as a memory, summarizing everything the network that has been sent so far in the sequence. The weight sharing across time is exactly what let RNN handle variable length sequences. Sometimes a regular feed forward network just can't do that. Okay, so speaking for which, why not just using a feed forward network? So feed forward network only accept the fixed sized input while the RNN handle the variable length sequential data. Okay, now the feed forward network has no memory. Every input is being processed independently while the RNN has some of the hidden memories that it can take in. And feed forward network completely ignore temporal order while the RNN explicitly model made for this only. RNN also opens the door for the extension like the LSTM, GRU, and other also that we'll be covering in upcoming lectures. Mathematically, at each step t, the hidden state is h of t equal to 10h of wxh times xt plus whh time ht minus 1 plus a bias term. The output is y hat t equals to the softmax of why times ht plus a bias. We train by minimizing the cross entropy loss summoned across every step in the sequence. For sequence to sequence task like the sentiment classification, we only use the final hidden state h of t to make the prediction. If you unroll an RNN in time, you'll see the same weight matrix Wx of h, Whh, and Why reuses at every single step with the hidden state passing forward from one step to the another. Moving forward towards section 2, the types of RNN and the gradient problem. So let's go through the RNN variant. The vanilla RNN is a simple recurrent and we just covered with 10H activation used mainly for short sequences and toy tasks. LSTM or the long short term memory introduces a separate cell state C of T and 3 gates, a forget gate, an input gate, and an output gate. The forget gate decide what old information to throw away. The input gate decide what's new information to add. The output gate controls what get exposed as the hidden state. So this gating structure is specifically designed to prevent the long range dependency. GRU, gated recurrent unit, simplifies this. It means that the cell state into the hidden state and uses just two gate, an updated gate and a reset gate, giving simpler performance to LSTM but with fewer parameters. Bidirectional and the bilateral RNN process the sequence from both forward and backward, giving context from both the direction, which is great for tasks like name entry recognition. Deep RNN stack multiply recurrent layers for higher level temptation, abstraction, and encoder decoder RNN use two separate RNN, one to encode an input sequence and one to decode it into new sequence, the backbone of the machine learning and sequence to sequence task. Now we know that why is the need for the LSTM and GRU. When it comes down to vanishing and exploding gradient, when we backpropagate through time, the gradient at the very first hidden layer involve multiplying together the gradient at every step and at every time step. In a vanilla RNN, this repeated multiplication by WHH and the 10H derivative cause the gradient to either vanish or explode over a long range. So at that time, LSTM and GRU are being used that create nearly linear path for the gradient to flow through it. We have the section 3 with design, training, and the application about it. On the design side, hidden size control the memory capacity, typically somewhere between 64 to 1024 depending on the task. Sequential length set the context window. Long sequences are hard to train, while we often capture it using truncated BPTT. For each cell, LSTM or GRU is preferred over vanilla RNN in almost all practice settings. Usually, 1 to 4 layer captures high level temporal features as quick parameter example. For example, a vanilla RNN with the input size of 100, hidden layer of 128, and 10 output classes comes out with 30,600 parameters. LSTM roughly multiply that by 4, GRU by about 3, and because of their extra grade, this can happen. Okay, now for the training part, gradient clipping caps the gradient norm to prevent exploding gradient, typically clipping the norm between 1 and 5. Truncated BPTT only backpropagate as a limit number of steps back, keeping training truncated on long sequences. Teacher force feeding the ground truth previously output during the training into sequence to sequence model. Later, layer normalization stabilize the hidden state distributing across timestamps, and recurrent dropout applies dropout consistently across time rather than resampling it every time. And of course, early stop based on the vanilla loss help preventing overfitting to the sequence. So now we have seen that where what RNN is. Now we need to know that where RNN is being used in the practice. Language modeling, predicting the next word or the character. Machine translation using encoder decoder RNN. Speech recognition, mapping audio frames to text over time. Time serial forecasting like the stock price or the weather. These are the places where RNN are being used. To wrap up, RNN process sequence using a shared, repeated, and updated hidden state. Vanilla RNN struggle with vanishing and exploding gradient over long sequence, while the LSTM and GRU solve this problem using gating mechanism. So that's all about the video for the RNN. We'll be